welcome to Aerotech's Automation1 Motion Control Platform Educational Series. Aerotech is a company that solves your toughest precision motion and automation challenges. Automation1 is a motion control platform consisting of software-based controls and development tools, PC and drive-based control hardware, and hardware-based drives for servo motors and other devices. In this video, you will discover what the Harmonic Cancellation feature of the Dynamic Controls Toolbox is and how it can be used to improve your system's performance. My name is Alex, and I'm a Control Systems Specialist for Aerotech. The Dynamic Controls Toolbox is a series of optional purchasable controller features that supply algorithms and tools that can improve the motion performance of your stages. You will often hear these referred to as DCT or the DCT tools. There are a few different tools within the Dynamic Controls Toolbox. In this video, we will touch on just one, and that will be the Harmonic Cancellation Toolkit. So what is Harmonic Cancellation? Harmonic Cancellation is a control systems tool that has the ability to reduce the tracking error of repetitive sinusoidal systems. Take, for example, an unbalanced load on a rotary axis spinning at a constant velocity. This unbalanced load, or any load that is not perfectly centered on the axis of rotation, will inevitably induce some sort of sinusoidal error in the rotary system. Harmonic cancellation can attempt to reduce these repetitive errors by acting as an additional component of the servo loop in an attempt to reduce and reject the desired frequencies. So what uses are there for this? Well, in theory, harmonic cancellation can be used when any inputs into the system are periodic. These include when the desired trajectory is periodic, the system may not be tracking due to periodic disturbances, there are torque disturbances due to cogging or ripple in the motor, or there is a mass imbalance on another axis that is moving. Lastly, we should note that the Harmonic Cancellation Toolkit allows for rejecting up to 5 of these harmonics per axis. And we'll see an example of that next. Take, for example, this image from our white paper document on the subject. Here, the system designer was using a horizontally mounted rotary stage and needed to improve the velocity stability. Because of how the system was configured, there was a noticeable once per revolution error due to the payload, as well as some error introduced by the 9-pole motor pitches per revolution while operating at 60 RPM. Basically, what we're seeing is a once per revolution error as well as some influence from the motor poles themselves. In this example, applying the harmonic cancellation algorithms at these different frequencies allowed us to reduce the tracking error from 33 to 1.7 arc seconds, a 12 times reduction in the actual position error. Lastly, as you may have noticed, the Harmonic Cancellation Toolkit allows us to apply and reject up to 5 of these harmonics per axis. This is essentially what we're seeing here in this picture, where we see a main and primary harmonic, as well as some additional smaller harmonics occurring at the same time. Harmonic cancellation can be used on both of these frequencies simultaneously on the same axis to reduce the total error that the axis may be seeing. Now, as we mentioned before, there are a number of different applications that harmonic cancellation can help with. More specifically, this can include force and torque disturbances such as ripple disturbance, cogging torque, and unbalanced disturbance or mass imbalances. Sensor testing is another application, as well as sensor error mitigation, disk drive tracking, E-chain errors, or just contouring spindle speeds. So how does harmonic cancellation work exactly? For a much deeper look into this and the theory behind harmonic cancellation, I'd highly recommend reading through our white paper on this subject. This can be found by searching Harmonic Cancellation Algorithm on our website. The link was also provided here. In short, harmonic cancellation is an algorithm added onto the typical control loop that introduces additional components alongside the PID controller. This addition allows us to reject the periodic disturbances injected into the control loop indicated by our error here, DS. Because harmonic cancellation is simply an add-on or plugin, this allows it to be easily enabled and disabled without needing to affect the configuration and tuning of your PID loop. This in turn means that we are not going to be changing the baseline servo tuning performance of your actual system. Now, this is not to say that harmonic cancellation cannot negatively affect the performance of your system if it is incorrectly configured. In fact, certain settings could cause the harmonic cancellation algorithm to go unstable if it is not correctly set up, but we will touch on this later. To set up harmonic cancellation, you will need to configure 5 types of parameters: the type, the input, the period, the gain, and then finally actually turning it on and off. Each of those are going to be indicated by the parameters you see here. Let's start at type. Automation1 has 2 options for the type of harmonic cancellation that you choose to perform. These would be frequency or position-based. The first is frequency-based. We will use this to reject the disturbances that are always at a specific frequency. A good example of this is an axis that is commanded to move in a specific cyclical pattern, like a rotation or oscillation of a spindle. The second type is position-based. We will use this option to reject all the disturbances that change their frequency based on the speed of the motion. A good example of this is an unbalanced load on a rotary axis, where that rotary axis could be changing speeds. Or another example could be the pulling and tugging of a cable on a linear axis. After you have your type, you then need to specify your input and period. Based on if you're using the position or frequency type, this will determine if you need to configure both the input and period settings or just the period setting. Again, we will go through all of this in our example just to give you a more first-hand look. The input specifies where the input of your position type comes from. For this, you have the option of selecting the position command, position feedback, or auxiliary feedback. This, however, will only apply to the position harmonic cancellation type. The period option specifies the period of the disturbance you need affected by harmonic cancellation. This will be different depending on which harmonic cancellation type you actually configured. If you are setting up the frequency type, you will only need to configure the period parameter. This will represent the period of the signal in seconds that we are canceling. For this harmonic cancellation type, you don't need to configure the input parameter. If you are setting up the position type, you will need to set up both the period and the input parameters. For the period parameter, you will enter the period of the signal in encoder counts. So essentially, when used with the frequency type, your period will be the period of the signal you cancel in seconds, but while you are using the position type, your period will be the period in encoder counts. After you have your type, period, and input parameters correctly configured, then you need to configure the gain. This gain represents the conversion rate of the harmonic cancellation algorithm on the frequency that you wish to reject. In other words, the rate of change that harmonic cancellation has on the system. You can think of this somewhat like a learning rate. The higher your gain, the faster the harmonic cancellation tries to, quote, learn and reject this specific frequency. Figuring out the best value to use in your system may require some trial and error, though. A good starting point is to start a value of 1, then try increasing to a value of 2 or 3 and see if you can further reduce the error. Now, as we touched on earlier, this is where you could cause the system to go unstable by improperly configuring the harmonic cancellation. Setting this gain too high could cause the harmonic cancellation algorithm to actually go unstable. So this is just something that you'll need to be aware of when trying to figure out what kind of gains you plan on using. You should also keep in mind that when you are using more than one harmonic of a specific base period for your axis, we recommend that you set the gain for each of these harmonics to the base gain multiplied by the number of the harmonic. So for instance, if your fundamental harmonic is at 10 Hz and you have a gain of 1, and your next harmonic is then at 20 Hz, set your gain to 2. Or if your base gain at 10 Hz is 2, and you have another harmonic at 20 Hz, set your 20 Hz gain to 4. And then finally, we can use the harmonic cancellation setup parameter to enable or disable the harmonic cancellation algorithm. Now I know that was a lot of information all at once on the parameters, but here we can see a quick diagram showing which parameters need to be set up based on the type of harmonic cancellation that we choose on doing. So we can see for the frequency type of harmonic cancellation, we do not need the input parameter, but we do need to set up the period and then the gain. Likewise, for the position type, we can see that we need to set up both the input and the period parameters. Alright, now that we've gone through that, let's go through a quick example to show you how to configure and demonstrate harmonic cancellation. For our example, we'll be using one of Aerotech's Automation1 demonstration kits. To give you an example of what this will look like, we'll include an image for reference. Essentially, this will just include an unbalanced weight mounted on a rotary axis. We will then attempt to rotate the rotary axis at a constant velocity and apply harmonic cancellation to reduce the tracking error from that rotary axis. And hopefully by doing this, we'll be able to see a reduced tracking error on the rotary. So let's first just run through and show you where the harmonic cancellation parameters are located. So like the other parameters, if we go to the configure workspace and go down to optimization, we can scroll down until we find the harmonic cancellation parameters. Here we find the setup, the type, the input, the gain, and then the period for each of the 5 different harmonics that we can try and reject. So for our example, what we're just going to simply do is enable our y-axis with our offset load and execute a free run command at a fixed rate. So while doing this, we should be able to see some kind of periodic once per revolution error occur in our system. And that is what we can try and use harmonic cancellation to try and reject. So we'll use our visualize workspace to configure and capture a plot for the position error, velocity command, and current feedback of our axis. So here we can see that once per revolution error occurring as a result of the unbalanced load. Now, using our cursors, what we can actually do is try and figure out what that period is. Now, because we are just doing a once per revolution movement at 360 degrees per second, it's pretty easy to do the math and figure out that that disturbance is occurring every 1 second. But if we were to change that frequency to, say, half or even double, that period is going to change, and then we'll be able to correct for that in our harmonic cancellation as well. For this example, so we'll just have to go in when we edit our harmonic cancellation parameters, we'll just remember that our period is a period of 1 second. So we'll select this as the frequency type. Because we're doing the frequency type, we don't need the input. For our gain, we're just going to use a gain of 1 and see where that takes us. And then we come to the period input. So like we mentioned, the period input, that's going to be how often that disturbance is occurring. And because we are using the frequency type, this is going to be in seconds. So we already know that it's happening and occurring every 1 second. We'll go ahead and enable, make sure that we did this on the correct axis, save, and reset. Now we'll start the movement back up again. And once that hits constant velocity, we'll take another plot and compare that against our baseline. So there we can already see the plot is much different than before, and that is as a result of us trying to cancel and eliminate and reject that disturbance. So what we can do is use the overlap plot feature and overlap that with the other plot that we just took. So here we can see the larger in orange oscillation that we're seeing. That is our once per revolution error, and then the blue line is going to be our post-harmonic cancellation. So that is showing you that since we've implemented harmonic cancellation, we have drastically reduced what our actual following error on that axis is. But we have to keep in mind that this is only doing this at a set period, at a set frequency, in this case, every 1 second. If we were to change our speed to, say, half, we would see our position error looks a little different. We could even overlap that with the previous 2 plots we took, just to show you what it looks like. So this center one, obviously, that is going to be our 360 degrees per second. We are correctly trying to reject that harmonic. The more fuzzier blue one, that is going to be our half speed. And it, obviously, because it's operating at a different frequency, we're seeing a bit of a different error. We're not quite rejecting that correctly. So that is where the position harmonic cancellation type comes into play. So now for setting up the position harmonic cancellation type, we'll just have to go back into the configure workspace, set our type to position, say we want to cancel the feedback that's coming in. We'll still stick with a gain of 1 just for simplicity and see how well that looks. And now this is where our period is going to change. So now, because we're under the position type, this value here is no longer in seconds. Instead, this is in encoder counts. And what we want to do is we want to try and reject a once per revolution disturbance. So for that, we're going to need to figure out for this motor, what is 360 degrees in encoder counts. Now there's a couple ways you could go about doing that. One, you could go to your counts per unit, find your counts per unit value and multiply that by 360. Or we can go here into feedback and look what our primary feedback resolution is. So for a rotary axis, this primary feedback resolution is your number of counts per revolution of the motor. So that makes it pretty simple on us for our example. So we'll just take that value and paste it in here. Now we'll go ahead and save and reset. And we'll start with moving this actually at 360 degrees just to show you what the rejection plot will look like. And then we'll drop that down to 180 again just to show you that even at 180 degrees, it is still rejecting that disturbance. So here's our 360-degree revolution per second revolution. And we'll drop that down to 180. And take another plot here. Now let's take that plot and compare that against what our 360-degree plot was, which was plot 31, and our original baseline plot of plot 28. So here we can see now that we are actually correctly rejecting the disturbance at once per revolution and not at 1 hertz or 1 second, we do get a much more consistent and a much neater looking position error. So we still have that, original baseline error, but now we can see that even as we change our speed, so the darker orange is going to be our 360 and our blue is going to be at 180 degrees. And we can even see that showing up in the current feedback as well, where our period of our oscillation looks definitely expanded more and looks longer because we're doing it at a slower speed. So this just goes to show how you can use both different types of harmonic cancellation, both the frequency type and the position type, to try and reject and reduce the position errors that you're seeing in the system as a result of these kinds of unbalanced loads and movements. That concludes this motion control platform educational video. Thank you for watching, and I hope you enjoyed learning about what harmonic cancellation is and how it functions.